All right, it's finally time to dive into visual perception. And this first topic on visual perception will include some videos on just the basics of vision, starting at the level of sensory receptors and some of that early processing. Then in the following topic, we'll get further into the higher level perceptual processes related to seeing, to the experience of vision. So early in the course, we saw this overview of the perceptual process. And at that time, I mentioned that a surprising amount of what we perceive does come from these early steps, these early few steps in the perceptual process where that proximal stimulus, a pattern of light, hits the back of our eyes, and some processing occurs around those sensory receptors. So for this video, that's what we're going to focus on. Let's start by just kind of zooming in on the eye a little bit. First off, as the light comes in from the outside world, it passes through some stuff at the front of our eyes. So this is the front of the eye here, the light's coming in. For example, the light gets focused by the cornea, an outer layer at the front of the eye. It goes through the pupil. That's the opening where your iris muscles kind of open and close to make the pupil larger or smaller. And then the light passes from there through what's called the crystalline lens. We'll just call it the lens, which also helps focus the light so that it hits the back of the eye in a clear way. Now, the middle of the eye, the whole kind of meat of the eye is filled with a liquidy gel called vitreous humor. Basically, the light just passes through that. And then at the back of the eye, it hits the retina. So kind of drawn in orange or yellowish at the back here, that's the retina. It's a layer of neurons at the back of the eye that includes the sensory receptors for visual perception. So it's that thin layer at the back, and from that layer, from that retina where some neurons were processing the info, the neurons will project axons out the eye, out the back of the eye, through the optic nerve. So this area here, it's a bundle of wires kind of heading from the eye to the brain. You can see it coming out the back. Now, at the very back of the retina, so if we zoom in on the retina here, zoom in on that little layer at the back of the eye, at the retina, if we zoom in on the very back of the retina are the visual photoreceptors, the visual sensory receptors. We call those rods and cones. They transduce light. They turn into neurons firing. So you can see them in kind of red and purple here at the back, the farthest back layer of the retina. So that means the light has to pass through those other layers of gunk, all those other cells that we can see, before it actually hits the photoreceptors and becomes neural firing. And those other neurons nearby, the ones right in front of the photoreceptors, we'll see that they process the output of the rods and cones, and they are what send it to the brain. So basically, the light is going to hit these rods and cones, then get processed by some of these other, we'll call them kind of support cells or nearby neurons, and then it's going to go out the optic nerve. Then these fibers, these axons, are going to go out the eye towards the brain. Now, rods and cones are named that simply because of their shape at the tip. So you can kind of see in this microscopy picture in the top middle here, rods look like big cylindrical rods and cones have a more pointed cone-like tip. All of them are filled with proteins called opsins, just have a light-sensitive bit inside called retinal, which is actually a form of vitamin A that's sensitive to light energy that activates when a photon of light hits it. Now, rods and cones are actually specialized for somewhat different visual functions. For example, rods are especially important when seeing in dim light, like at nighttime, whereas cones are less involved in dim light but very active in normal lighting during the daytime. Rods basically just turn on or off if they're hit by light, but by themselves, they can't really distinguish between different colors. They're confined to basically just black and white vision. On the other hand, cones are what give us color vision. We actually have 3 different types of cones, sensitive to different wavelengths of light, different types of light. And the colors that we see come from what combination of those cones happens to be active, what combination of those cones is going off based on the wavelengths of light that are hitting our eye. You can kind of think of it like one type of cone is sensitive to what we might perceive as red, another is more sensitive to what we might perceive as green, and a third type of cone is sensitive to light at wavelengths that we might usually perceive as blue. Now, there are other differences between rods and cones. So another difference is that cones are really essential for seeing detail, for having a lot of acuity and sharpness to our vision, like being able to see the difference between the shapes of one letter or another letter when your eyes are focusing on a word while you read. That requires cones. Meanwhile, rods kind of suck at detail, suck at sharpness, but are much better at picking up big picture information. Like they're good at kind of noticing the overall shape of things, what's happening in your overall visual field, big changes, big patterns, and they're pretty sensitive to motion as well. You can think of it like this. Your rods will quickly tell you that something big is suddenly approaching from your left side, while your cones will help you identify it as a tiger and allow you to count how many orange and black stripes are on it. Right? That's a detail thing, assuming the tiger hasn't eaten you by then. Finally, related to that last point, rods are really important for processing things, often our periphery, off to the side where we're not currently focusing our eyes, while cones are much more involved in processing what we're currently focusing our eyes on. Specifically, there's tons of cones found at the very middle of the retina, straight back from whatever you're pointing your eyeball at, in a place called the fovea, a place that's just super dense with cones for getting lots of detail from whatever you're focusing directly at. So here's another angle on the eye in this diagram here, like if we're looking down on the eye from above. And again, the retina stretches all along the back of the eye here, a thin little layer at the back of the eye. The cornea and lens is up front here, and light comes in, and it's going to go straight back, right? Whatever you're looking directly at will go straight back and hit the very back of the eye there, what they've labeled the fovea at 0 degrees on this image. That's right where light comes directly in, not off to the side at all, so it's 0 degrees off to the side. It's actually a pretty small area. The fovea is about 1.5 millimeters wide. So if you're looking at, say, a tree that's 50 meters away from you, light from that tree is going to hit your fovea, not off to the side. But if there's a big truck way off to the left of the tree where you're not focusing, then that truck's light is going to come in at an angle, right? And so it won't hit the fovea, or it might come in at kind of an angle like this, and it might hit somewhere like that 40-degree mark off to the side. But that means it won't be seen in as much detail. It's off in the periphery where the rods are going to get it. So then the rest of the retina, so if the fovea is at 0 degrees at the back here, the rest of the retina off to the sides is called the periphery of the retina. And that's just because it picks up light from our peripherals, right? From our periphery, off to the side of where you're looking, off to the side in the visual field. So in other words, the rest of that is what gives us peripheral vision. Now, two of the most common forms of blindness involve either damage to the fovea or damage to the periphery. So for example, macular degeneration is a pretty common condition where the area around the fovea stops working. This is often as a result of age, so it's called age-related macular degeneration, and it leads to a blind spot wherever you focus, which means you basically can only see things off in your periffs, which also means trouble getting detailed vision, trouble being able to read things, stuff like that. Really, this picture on the left, to demonstrate it better, should show things further out from the center being blurrier, to emphasize that we don't get all that detail off in the periphery. We only get it in the fovea, where our cones are kind of densely packed right in the middle there. All right. And then there's a different common cause of blindness. It's called retinitis pigmentosa. You think of it kind of like the opposite. It's a progressive genetic condition. It attacks the rods in the back of the eye, so it causes a loss of peripheral vision as well as poor night vision, because we saw rods are important for seeing in dim light, right? It causes a sort of tunnel vision where someone can basically just see the part of the visual field they're focusing on, but they lose the periphery. Like you couldn't see someone approaching from off to your left side. So macular degeneration and retinitis pigmentosa are damages to those two parts of the retina that we've talked about, the fovea versus the rest of it, the periphery. Now, let's look back at that image of the eyeball here where they've labeled the retina by how many degrees each part is from the fovea at the center. What we've graphed on the right, this diagram on the right here, is how many rods and cones there are at different parts of the retina. And you can see it's counting by like tens of thousands per square millimeter. So we do have lots of them in there, but we can see how dense they are at different parts of the retina. So 0 degrees here, that's the fovea. 20 degrees to the left, that would be at this part of the retina, and so on. So if you look at the graph at 0 degrees, at the fovea right in the center, what you see is the fovea is all cones, right? The blue lines are for rods. They go down to 0. You have no rods at the fovea, but we have this big spike for the red line, which is cones, a bunch of cones all right there in the fovea. It's a much smaller number of cones kind of spread along the rest of the retina, along the kind of thin layer along the side of the retina. There are some cones, but not very many. Whereas in the periphery, so all along the sides there, it's mostly rods. As you can see from the blue line here, right? They way outnumber the cones, in fact, overall in our eyes. So we have about 6 million cones total, but 120 million rods. And you can see that by just how high the blue graph gets versus the red graph, right? Total number, way more rods. Now, also notice the big brown bar here on the graph. That corresponds to where the optic nerve exits the eye. In other words, this part here is what they're labeling in brown on this graph. At that spot, there are no photoreceptors. There's no rods and no cones at all, so both of them go down to 0. None of the light that hits this part of the retina, so anything coming in at just the right angle that lands right there, none of that light is going to get registered at all. We actually call this a blind spot. It's a portion of the visual field that we can't see, so anything at the angle that's directly out there that would land right back here, anything out at that angle is in the blind spot of our visual field. Just a part of the visual field we can't see because the light lands somewhere where there's no photoreceptors, no neurons that can detect light. And we've actually got one for each eye, since each eye has its own optic nerve coming out. So there's slightly different parts of the visual field that we're blind to. Now, let's demonstrate this idea of a blind spot so you can experience exactly what we're talking about. What you'll want to do for this demo is close your left eye. So look at the screen, close your left eye and keep the left eye closed. You might want to cover it with your hand or something so you don't have to open it. And now with your right eye, I want you to look at the X. So you're going to be probably looking a little bit across the screen, right? If you're looking straight on, your right eye has to cross over a little bit to look at the X. Keep looking at that X, and I want you to slowly move closer to the screen. Or if that doesn't have the effect, you might want to slowly back away from the screen while keeping your right eye looking across to that X. At some point, when you're at the correct distance from your screen, that dot off in the periphery will just disappear. If you move further back or further forward from that point, the dot's going to come back in. You'll see the dot again in your periphery. But when you're at the exact right distance, the dot will always disappear. And that's because it's coming in at just the right angle that it falls on your optic nerve, on your blind spot. It goes away. You don't see it there. You don't see anything at that exact angle of your visual field. Now, if this didn't happen to work on the screen you're on, that's okay. Like if you're watching it on a small tablet or something, you couldn't get it to the right distance. You can also do this demo by just drawing an X and a dot on a piece of paper. Make each one about a quarter of the way in, like you see here. It's a fun demo you can do with your friends or kids or whatever. And then do that same thing, just with your left eye closed. Use your right eye to look across at the X. Start the paper holding it out at arm's length and just slowly move it closer to yourself until the dot disappears. If you go too far, move it back out a little. At some point, you'll find the dot disappearing. That's your blind spot. The reason you can sometimes see the dot and sometimes can't is just due to that angle. So at most distances, the dot comes in at an angle where its light is going to land somewhere on the retina, somewhere on the periphery off to the side of the fovea. Since it hits the retina, it gets picked up by the photoreceptors and we see the dot. So you can see that example here. When something's literally far enough away from you, this is the actual physical stuff in front of you. The dot is coming in at such an angle that it definitely lands on some retina, on some photoreceptors back here. So this up here in gray would be what we perceive. This is what we see when it's held at a long enough length away from us. But when we get closer, when we get it to just the right distance from the screen, so we've brought the stimulus closer to our eyes, just the right stimulus, so that the angle of the light coming in from that dot happens to be just right to land on the blind spot where there's no photoreceptors, our experience is what you'll see here in the gray bubble. We perceive the cross, but not the dot. Now, the question is, if we have these blind spots, why the hell don't we notice the blind spot throughout the day? Like, why doesn't it distract us all day long that we got a little bit of the world missing on each side? And for one thing, the blind spot is at a different place for each eye, right? A different angle coming into each eye, which means whatever stuff is out there in the world is landing on your left eye's blind spot maybe, but that means it'll actually still be hitting some real photoreceptors in your right eye or vice versa. So even when something's hitting the blind spot in one eye, it's hitting some photoreceptors in the other eye most of the time. So that might explain why we don't notice it, but even when we close one of our eyes, so let's say you've only got one eye, you close the other one, even then when you look around at things with just one eye, you don't seem to notice the blind spot, right? You don't notice that we're completely missing a big old chunk of the visual world. So the mystery remains. Why don't we notice it? Why don't we see a big hole in the middle of our visual field? It's because something pretty freaking weird is going on here. although you may not have noticed it during the demo. When that dot disappeared, when you're doing that blind spot demo and the dot disappeared, what did you see where the dot was? What do you see at that part of space when the dot does disappear? Do you see a hole? Do you see a nothingness? Do you see a void or a complete lack of sight in that spot? No. A complete lack of sight would be what you're experiencing right this moment in terms of seeing behind your head. You don't have any visual experience for what's behind your head right now. It's just not there, right? But when we do the blind spot demo, we don't get that. We still have a visual experience where the dot previously was, but now instead of the dot, we see white. We see the same as all that surrounding background color. And actually, if you do this with a purple background, you'll see purple where the dot was right before it disappeared. The brain fills in that area of the visual field using its best guess from surrounding information. Let's try it. Once again, close your left eye, and with your right eye, look at the X. Then move your head or move your screen if you're holding a screen. Move it until you're at the right distance, and that dot will disappear. And this time you might notice the dot gets replaced by green. It becomes a uniform green field over there. Your brain makes it up. There's no actual green at that part of the screen, but your brain guesses that must be what's there because everything around it is green. Finally, just to show this filling in procedure or this filling in phenomenon, let's do one last version of the same thing. This time, do it opposite eyes, so close your right eye or cover your right eye. And now with your left eye, look at that cross off to the side, off on the right side. So you want to, with your left eye, look across to the right, look at that cross. As you get to the right distance, you might have to move back and forth. When you get to the right distance, that open hole in the middle of this picture, this kind of wheel of spokes or whatever, that open hole in the middle gets filled in. Like the spokes of a wheel continue across the middle. Your brain just continues those white lines as if they go all the way through. That's your brain inventing, indeed hallucinating a visual experience in the part of the visual field where it's getting no input from the sensory receptors. It just makes up the best story, the best guess of what's out there. And since those white lines seem to continue on each side of the blind spot, the brain assumes they are continuous going through the blind spot, so that's what it invents, and that's what you perceive. This 1 minute clip from YouTube is a kind of fun, even weirder version of it. This guy, he's a psychology researcher and actually a former magician named Richard Wiseman. He's published some really cool studies. He's going to, in this demo, make his head disappear when it's in the blind spot. So you'll need to, again, move toward or away from your screen until his head disappears. And your brain is going to fill in that place with just the background. But notice what happens when he then moves a bar through that space.
We're going to perform the amazing vanishing head illusion in less than a minute. Here we go. You need to sit back from the monitor and cover up or close your right eye. Now with your left eye, stare at the cross next to me. Now keep on looking at the cross and slowly move towards the monitor. And at some point, my head will appear to disappear. When that happens, stay exactly where you are. It's an incredible illusion. You'll still see my body, you'll still see my hands moving, but my head just won't be there. What's even more remarkable is as I move this up, you'll see a continuous black bar where my head should be. It's a great illusion and just goes to show what you can achieve in less than a minute.
So not only does your brain fill in the orange background, but it also fills in that moving bar, despite the fact that as the bar passes through that area, your eye isn't getting any input from that part of space. All right, let's get back to the eye stuff. I mentioned before that both the cornea and the lens at the front of the eye, they focus light as it comes in. The cornea actually does most of that work. It does about 80% of the focusing, but limitation, it has a fixed shape. It can't adjust in any way. The lens, on the other hand, only does 20% of the focusing, but it has the ability to change shape, to adjust as needed. And we'll see that's really important for things like focusing on stuff that's near or far. So when I say these parts, the cornea and the lens, focus light, I mean what you can see happening here in the picture. In your eyes, just default, relaxed state, when you're looking at something far away, light coming in from that faraway object will be coming in pretty much parallel beams, as you can see here, right? If it's far enough away, they're basically parallel. And as those hit the eye, the cornea and the lens are going to focus those parallel beams so that they all end up landing on the exact same point on the retina, what they've labeled A here. That's good. That means for something straight ahead, they'll get focused right onto the fovea so we can see it very clearly, make out detail. But now think about what happens when an object is moved right up near your face. So when the light from the object that close is coming in, it's going to be coming in at various angles. Like you can see here, that means it's going to get focused by the cornea and lens, but it'll end up kind of with those beams landing at slightly different parts of the retina, right? They're going to focus too far back. So when they actually hit the retina, when they hit the retina here and get absorbed, they're hitting different parts. Light from the same target is landing at various different places on the retina, meaning you're going to get a blurry sort of experience, which is bad, right? But thankfully, our eye has a trick to avoid this issue happening. So when something's up close to us, our eye can do something to avoid this problem that we're seeing here. So for nearby objects, we can actually adjust our focus toward the object. What that actually means is the eye muscles squish the lens to change its shape, to adjust its focusing, so that those beams of light from the nearby object will again land at exactly the same place, which is what we want, like A here, so that they land right at the same place. That avoids blur and assures we can see nice detail for whatever we're looking at up close. That process, that adjustment of the lens to help us focus on something up close, that's called accommodation. It's the lens changing its shape to focus for near sight. That's why, despite the lens only doing 20% of the focusing, its flexibility makes it really essential for us to be able to see things at different distances. That said, even with flexible adjustment of the lens, sometimes that's not enough to see things clearly at various distances. For example, some people are nearsighted or farsighted. So what causes that? Well, let's first talk about nearsightedness. The technical term for it is myopia. When I say nearsighted, I mean that people with myopia can focus on nearby things just fine, but things far away are blurry. So their eyes are limited to near sight when we say they're nearsighted. Their eyes just won't focus well on objects at a distance. And the cause of this just has to do with the angles of those beams of light coming into the eye from objects that are far away. So let's say, for example, if the eyeball is too long, that means the beams will hit a point too early, right? They'll come to a point, but they'll come to a point too early if the eyeball is too long. And that means that by the time they get to the retina at the back and get absorbed, they've spread out again, which is going to cause that blur experience. Or if the cornea or lens are shaped imperfectly, so sometimes people have a condition where their cornea isn't shaped in a nice perfect angle there, that can bend the light too much. Same thing, it makes the light meet too early, and so by the time it gets back and hits the retina, it's spread out again, it's blurred again. Thankfully, that means this can be fixed simply by focusing the light differently prior to hitting the eye. So using corrective lenses like glasses or contacts, or it could be fixed by surgery like LASIK to adjust the cornea's shape. So myopia, at least, it is fixable. On the other hand, there's what's called hyperopia, the opposite, which is farsightedness. That means you can see things far off just fine, but things close up are blurry. And this can happen, for example, if the eyeball is too short. So the beams of light would meet too far back, right? Where they're going to meet is too far back. So instead, by the time they hit the retina, they're still too spread out, causing that blur. Now, this isn't necessarily a problem for younger people because young eyes can use accommodation, the squishing of that lens, to compensate. And they can still focus on things up close just fine. But as we get older, the crystalline lens, the lens in the eye, actually hardens over time. It becomes less flexible. So older people, older humans, can't accommodate nearly as much. They can't adjust their lens to focus differently. So they have trouble doing that close-up focusing that we saw before. This makes things like reading really challenging. So you'll often see older people hold objects further away to read them, or else they'll need reading glasses that focus the light based on close distances. But that means they have to take the reading glasses back off if they want to focus far away again. Now, if you want to experience accommodation yourself, to kind of see how your eyes focus the light on near or far objects onto the fovea, try this little trick. Grab a pencil or a pen. So if you have one sitting around, look around, grab a pencil or a pen, and you'll want to face the direction where you can see some things off in the distance. So you may need to turn away from your screen or even look out a window for this demo, but it's pretty simple otherwise. What you'll do to start is just hold the pencil up at arm's length and close one of your eyes. So keep the other eye closed. With your open eye, I want you to look past the pencil, not at the tip of the pencil, but just past the tip of the pencil at some object that's far away, like 20 or more feet away. Focus on the faraway object that's behind the pencil's tip. While doing so, notice the pencil point without actually looking at it. In other words, keep focusing your eye on the faraway object, but just kind of note your experience of the pencil point. The point will be blurry. Next, what you might do is slowly move the pencil toward you while still looking and focusing at the faraway object that's behind it. So the pencil point is going to become even more blurry when it gets closer to you. Like if it's just a foot away from you, it's going to be pretty blurry as you're looking at the faraway object behind it. It's right nearby to the angle you're looking, so its light is hitting near the fovea, but it's blurry because your lens hasn't accommodated to that close-up distance. But finally, with the pencil about 1 foot away, now shift your focus from that far object behind it to the actual pencil point itself, the tip of the pencil. Now actually look at the tip. It should appear sharp and clear. That's you accommodating. That's your eye adjusting. But now you'll notice the far away object that you were looking at before is out of focus and blurry. We can only focus close up or far away at a given time. That's because we're either squishing the lens or we're letting it relax at any given time. So that's a demonstration of that idea of accommodation, how your eye normally handles these things. All right, that's enough about the eye itself. In the next video, we'll actually dive a little deeper into the transduction process and how rods and cones do what they do, like why rods are so much better in dim lighting or why cones are necessary to perceive color.